Hi guys, I'm Huanfa, and today I'm going to talk about the real-time forecast of high street footfall using a case study of Bath. And apologies for not being able to share my video because of some technical problem. So this is an outline to my talk. And first of all, I would like to introduce something about the footfall research. So in recent years, the census provides some variable opportunity to study the granular human behaviors, including footfall in high streets or in the city. And understanding the footfall is important as it tells us about the visitor preferences, their motivations, and whether the marketing strategies are successful. And so far, there has been limited research being done on the prediction of the real-time footfall. And that's the motivation of this study. And so if we think about the footfall, there are different types of footfall and there are different questions that we can extract from the footfall data. For example, if we think of the footfall at a fixed location, like using a footfall counter for a specific location, we can know how many people pass this location at a specific time. And if we have the footfall data between locations, we can know how many people traveling from one location to another. And using the footfall data, we can understand like how many people pass this location. And if the data is very comprehensive, we can know like who passed this location and why they passed this location. And we can also understand the influence of different factors like the weather or the holiday on the footfall number. So in this research, we're interested in forecasting the footfall in a specific location. So we try to predict the next hour footfall in fixed locations using some data-driven models and the historical footfall. And we also try to understand the contributions of different factors for the footfall number. For example, the internal variables like the road dependence and the external, like the weather and holiday effects. So this is the case study area. And thanks to the CDRC and the Movement Strategy Company, we have the 2-year hourly footfall data from 10 cameras in the high streets of Bath. And the data is from 2017 to 2019. Here you can see the locations and cameras. And first of all, I'd like to give a sense of the data. So here it shows the daily and the weekly pattern of the footfall time series in different cameras. So we can see that in each day, the peak of the footfall is at 12 p.m. And if we compare the footfall in different days, so Saturday is the peak of the footfall number. And so the weekly pattern of the footfall is also very obvious. And then we look at the monthly seasonality of the footfall. We can see that the footfall records in December are higher than the other month. But if we use the median footfall to represent the footfall in each month, so the seasonality pattern of the month is not very obvious because the median is quite close across all the months. And we also collect data from different sources. So for this task, we have the internal data, like the time series of the footfall. We also have the external data, for example, the daytime of each time slot and the weather and the holiday variables, including the bank holiday and the school holidays. And to compare different models and to evaluate the result, we use the root mean square error as the performance measure. So here we compare the performance of 4 different models, the seasonal ARIMA with external variables, the profit model from Facebook, and the LSTM, and also the XGBoost. For the first 3 models, you may know that they are very typical time series models. And the last one, xgboost, is a classical model for regression and classification. So some of you may wonder whether the regression models are suitable for time series tasks. So briefly, XGBoost model is a sequence of trees. It has high accuracy for regression questions and is also able to avoid overfitting. And is able to fit non-linear relationship between the variables. So if we think of the time series as a special regression problem, we can use XGBoost for questions. But in this model, we will use some of the regressors, the temporal lag terms as the regressors. And also, as XGBoost is not able to automatically identify the temporal dependence, we need to manually select the temporal lag terms and as the input for XGBoost. So this is the pipeline of the model building. We divide the data into training and testing, and we use the walk-forward cross-validation to tune the parameters in the models. So here we use the walk-forward cross-validation instead of standard cross-validation, because that the data are not identically and independently distributed in the temporal scale. So using the walk-forward cross-validation, we're able to consider the temporal, to exclude the temporal autocorrelation here. And we also tune the key parameters for each model using the grid search and walk-forward cross-validation. This is the table of the parameters for each model. And then as in terms of the input for different models, so for the first three models, we use the historical footfall as the input, as well as the external variables. And as said previously, for the XGBoost model, we need to manually select the time lag terms as the input. So here we use the daily, so we use the footfall of the previous 2 hours, and we also use the footfall of the same hour in the previous 7 days as the time series data for the XGBoost. So we trained and tested these models in 10 different cameras here. So here is the RMSE on the training and testing data. If we compare the data of these two plots, we can see the XGBoost has the highest accuracy across all different cameras and in both the training and testing data. So we can see that the XGBoost is able to avoid overfitting. And this also confirms the predictive power of the XGBoost for time series problems, and specifically for the footfall forecast. And so next to the XGBoost, the LSTM has also very high accuracy across different cameras. And our concern here is the low accuracy of the seasonal ARIMA here. So the seasonal ARIMA is the red bars here. So we think that the low accuracy may be due to the tuning of the parameters. So maybe the grid search is not very suitable, very optimal for the tuning of the ARIMA models. And moreover, we look at the importance of different features for this task. We use the feature importance from the XGBoost, which is defined as the number of the times a particular feature is used in the XGBoost model.
Can I briefly interrupt you, please? There is a message. You've got this little panel there which says you're sharing your screen. If you could click on hide, I think we could, yeah, that would help to see the slides. Thank you very much.
Yeah, thank you for the reminder. So briefly, we can see that the temporal dependence are more important than the other features. Like important features are the footfall in the previous 2 hours and the footfall in the week ago. But this doesn't mean that the weather features are not important here, because the impact of the weather may be included in the footfall of the previous 2 hours. So some conclusions of this study. We have constructed some models that can accurately predict the footfall in the next hour using the time series or the regression models. And the result here show that the XGBoost and LSTM has a higher predictive accuracy than the ARIMA and the Profit models. And we also look at the feature importance from the XGBoost, which confirms that the temporal dependence variables are more important than the external variables. we also have some directions for the research. So the first one is to use less features for this forecast. Given that the internal variables are more important, can we develop a model that merely uses the internal variables to forecast the footfall? And the second direction is the more dedicated model tuning. As I said, the grid search may be not optimal for all the models. We can try to tune the ARIMA model using the ACF and PACF plots. And we also want to compare the feature importance using alternative ways, because the one we use may be not the optimal one. We can use the permutation importance to look at the importance of different features. And the last one, we'll try to develop spatial temporal footfall forecast models that try to simultaneously predict the footfall at various locations. For example, using the graph convolutional network models. So here in this research, we forecast the footfall in different locations separately. And these are the references for this research, and we thank the CDRs in the movement strategy companies for providing the data. So thanks for your attention.
Okay, thank you very much. Thank you for this very interesting presentation. So everyone, if you do have any questions, please put them in the chat window now, and I'm going to post them to the speaker. And while we're waiting for questions to come in, I've had two things that sprung to my mind, which are less about the actual method and technical approach, but like, would you expect, now you've done this case study on Bath, would you expect the model generally to work in different geographical areas, either, for example, within the UK, where you've got differently structured cities, or even in a wider cultural context? So do you see that the specific geography might be a limiting factor to make this model easily adaptable to other areas? That's the first question. And the second question would be about how much would you be able to cater for special events, like, let's say, football games, or something that might influence this, as well as the indicators that you've already outlined, such as holidays or weather, or these kinds of indicators, like one-off events that might also have an influence on the actual model, and how well would the model work in predicting change behavior there?
Okay, thanks for the questions. So the first question is about the generalization of the model for different geographies and different cities. I think, so we have tested this model in Bath, but if we want to generalize the model to different cities, we need to get the data. So this is because these models are data-driven, and there's no very strong guarantee that it will generalize well to other different cities and different geographies. And so the second question is about the impact of some major events or other factors. Yes,
exactly. Some more unpredictable factors than the usual time of the year, when you have holidays that are repeatedly coming, etc.
Yes. So if we want to explain the impact of these variables, we will need to construct different models from the ones in this study. Because here the task is to forecast the footfall, and we're not focusing on the explaining the impact of other variables. So in the light of the impact of external variables, we can construct some explanatory models, incorporate these features, and to consider their impacts.
So we've got two questions now coming in. One from D2, who's asking, as you plan to include the spatial lag effects in footfall forecasting, how do you plan to balance the spatial and temporal dependency? That's the first question.
Yes, this is a very good question. So right now, due to the data limitation, we're not able to tell how many people move from one location to another. But I think it is possible to infer the people flow between different locations based on the data from the fixed locations. So if we can do that, we can include the spatial dependence into this model and try some spatial temporal forecast models. And there has been some models that can incorporate the spatial and temporal dependence into a forecast models, like the spatial temporal graph revolution models.
And then we've got a question from Terry. Sorry, my line is a bit interrupted. Sorry.
Is there another question?
Yeah, there's another question. So Terry Lines is asking about accuracy. Do you know what is the accuracy of the underlying sensor, such as counting footfall from camera images?
I guess there are several uncertainties from the footfall count. And so the data we got is the processed data with the footfall count of each camera for each hour. Therefore, we don't have access to the raw data. But one potential uncertainty is the repeated count of one person under one camera. Let's say if one person walks around one camera, they may be repeatedly recorded, and that can be one source of the uncertainty. And again,
I don't see any. Yes, sorry.
Okay, yeah, and we were trying to get more information about the uncertainty of the data by the data provider. That would be quite important for the accuracy of this model.